So just like we had properties for exponents, we also have properties for logarithms. Let's take a look at a few important properties of logarithms that you guys need to know. Make sure you get them in your notes. Property number 1, log base a of 1 is equal to 0. Okay, it doesn't matter what the base of this log is. Anytime you are logging 1, you are going to get 0. And let's think about why that makes sense. Rewrite this expression in exponential form. Well, recall that we take the base of the log, we raise it to the other side of the equation, and we set it equal to the value inside of the log. That would give us a raised to the 0 is equal to 1. And again, a is going to be some value that's going to be greater than 0. Any non-zero number raised to the 0 power is going to be equal to 1. Property number 2, log base a of a is equal to 1. Now again, let's think about this in exponential form. If we take the base of the log here, which is a, and we raise it to the first power and set it equal to the value inside of the log, we get a raised to the first power is equal to a. And that is also a true expression. Any number raised to the first power is equal to itself, its own identity. All right, property number 3. If log base a of x is equal to log base a of y, then x is equal to y. If I have two logs with the exact same base set equal to each other, they will be equal if and only if the quantities inside of the logs are equal. This one should look a little bit familiar. We had a very, very similar property for exponents. It's called the one-to-one property. And as you might be able to guess, this is called the one-to-one property for logarithms. Property number 4, log base a of a raised to the x power is equal to x, and a raised to the log base a of x is equal to x. These are our inverse properties. And if you're curious as to where these properties come from, well, they actually come from our composition of two inverse functions. Recall that compositions of inverse functions must always simplify down into x. In other words, if we plugged in f inverse into our function f, it simplified into x. Or if we plugged in f of x into f inverse of x, that's simplified into x as well. As we have said, exponential functions and logarithmic functions are inverses of each other. So f of x is a to the x, then that means f inverse of x would be log base a of x, right? These two functions are inverses of each other. I have an exponential function with a base of a, and I have a logarithmic function with a base of a. If we take the composition of those two functions, take f of f inverse of x, that means I plug in log base a of x in for x into my exponential function. That would give me a raised to the log base a of x. And because these two functions are inverses of each other, that must simplify down into x. All right? A raised to the log base a of x is equal to x. There was one of our inverse properties. And similarly, if we took the other composition, f inverse of f of x, this means I'm plugging in a to the x into my inverse function, right? Wherever I see an x in f inverse, I'm going to replace that with a to the x power. That gives me log base a of a to the x. Well, again, because this is a composition of inverses, what does that have to equal? It has to equal x. So there we have our second inverse property. Log base a of a to the x is equal to x. All right, so these properties are going to help us to solve some more complicated logarithmic equations. Let's see if we can't put them to use. Solve the following logarithmic equation. Here we have log base 2 of x is equal to log base pi of pi. Well, what jumps out at you here? Over on the right-hand side of the equation, we have log base pi of pi. Recall from our properties of logarithms on the last page that log base a of a is equal to 1. This entire quantity here, the right side of the equation, is equal to 1. And think about why that makes sense. Pi raised to what exponent gives me pi? Well, that's going to be 1. Pi raised to the first power is equal to pi. So this now gives me the expression log base 2 of x is equal to 1. Now that we have isolated this log, one way that we can solve is to rewrite this expression in exponential form. Here we have the equation written in logarithmic form. To write it in exponential form, we take the base of the log, we raise it to the other side of the equation, and we set it equal to the value inside of the log. This is 2 raised to the first power is equal to x. So what does that mean for x? X must be equal to 2. That is our solution to the logarithmic equation. Let's try another one here. 5 raised to the log base 3 of 3 to the x plus 25 is equal to log base 674 of 1. Wow, look at this. Log base 674 of 1. This seems like it could be really complicated. However, recall from our properties of logarithms on the last slide that log base a of 1 is equal to 0. 674 raised to what power gives me 1? Well, that's going to be 0. The whole right-hand side of the equation is going to be 0. Similarly, over here, I have log base 3 of 3 raised to the x power. That was another one of our properties, log base a of a raised to the x. What did that simplify into? That was one of our inverse properties. That is equal to x. So, this logarithm on the left-hand side turns into x. This logarithm on the right-hand side turns into 0, which allows us to rewrite our expression 5x plus 25 is equal to 0. Now we have a really simple linear equation that we can solve. Subtract 25 from both sides of the equation, and then divide both sides of the equation by 5 to get our solution. X is equal to -5. All right, let's try one more here. Here we have log base 5 of x squared minus x is equal to log base 5 of 6. The cool thing about this equation is that we have two logs set equal to each other with the exact same base. Notice that both of these logs have a base of 5. Because both of these logs have a base of 5, we can use the one-to-one property to solve. Remember, log base a of x equals log base a of y if and only if x is equal to y. In other words, x squared minus x must be equal to 6. So, what type of equation did we just generate? Well, here we have a quadratic equation. And how do we solve quadratic equations? We set them equal to 0, and we factor. In this case, our quadratic factors into x plus 2 times x minus 3, which is equal to 0. Setting each one of the factors equal to 0 and solving for x gives us x is equal to -2, and x is equal to 3. All right, so there we have a few quick problems using our properties of logarithms. Make sure you guys memorize those properties and look out for them when you are solving logarithmic equations.